Hi, hello. This is Dr. Prasad Putilam. We are on my YouTube channel, My Intuition 4865. I'm doing a video class series on a new topic of Visheshwara Technological University from 2025 2026 onwards. But that means 2025 admitted students onwards. A new syllabus is framed. A new course is framed for called as Applied Chemistry for Smart Systems with a subject code of 1BCHES102 bar 202. Means either it is in students will study in first semester or students will study in second semester. So 1021 represents first semester, 2 represents the second subject. 2 represents the second semester, and the another 2 represents the second course of their first year engineering courses. Okay, now the course outcome of this particular applied chemistry for smart system is given here. Very nicely framed course outcome. I am on to module 1. The syllabus of module 1 is given here. You can read it. Now I am touching on some of the topic in this particular class video. The remaining I will cover in the next videos. Okay, now the first topic, that is memory devices. I made this study material with the help of artificial intelligence tools available online available. Therefore, you can also try the same thing to get the study material. I made this material. I found it very interesting, so I'm giving an explanation from my side. Usually, it will be reading as such, because I made it in such a way that it can be read and understand what the content actually it says. Okay, so first topic, that is memory devices. A memory device, it is a very tiny electronic part which can set two states called the zero state or the one state. Actually, we call it as state A or state B. Just think of like a a water tap. When the tap is open, the water will flow like current flows. When it is closed, the water will stop. So the electronics, they read this flowing, similar type of the flowing as state 1, this particular state, and if it is not flowing, then it will read it as a 0. Okay, so now what decides the flow on such electronics? That is, the answer is materials. Which material, what type of materials, the chemistry of materials, which called as the material chemistry, material science, is very important, which will decide how fast it will go, how long it will remain, how many times we can use it, and how much energy it will give. That is called as the speed, the retention, and the endurance, as well as the battery life of that particular electronic device or material. Okay, now the atoms layer, that it can the atoms, the layers of atoms, it will decide how fast it can flow, how long it remembers the state, how many times you can write or erase before it wear out, or how much energy each operation needs. That is battery life. The second topic, that is organic semiconductors. Why the organic, what semiconductors really means? First, a semiconductor, it is a material which will either allow the material to flow, or it will block as we wish. We have the control of allowing the electrons to flow, allow the electricity to flow, or we have the control to stop the electricity to flow. Just like the green light, green symbol allows the vehicle in a road to go or move, or the red light which will allow the vehicle to stop. Okay, based on that, the semiconductor will work. Okay, then the behavior, this when to flow or when not to flow, it depends upon how we treat the material. Okay, how we treat the material, it again has got so many parameters to check when we prepare a particular material having that type of application. We have to check how much apply a voltage, shining the light, the heat, or the tiny amount of other chemicals to be added, which is called the dopant, or how to make a very thin layers which will work in this way. So this is why the chips, which can act like a switches or memory, that means the same piece of material can be made on or off as we wish. Now, what is this organic semiconductors is so special nowadays? Earlier we have studied the semiconductor, mainly studied which are silicon based semiconductors. Now what are these? Organic here means they are carbon based. The molecules, the base structure is made up of carbon, and of course hydrogen will be there, other elements as we wish we will be keeping to adding to that, but the main base structure is carbon. So any molecule which contains carbon we call it as organic. Okay, or just like a plastic materials are also organic materials only, but not silicon, that is called organic semiconductors. Now why we can make them into very thin film. Very thin film we can prepare with organic molecules even at a very low temperature, no need of going high temperature and all. Sometimes we can make it as a printing one. We can make the organic molecule as a ink, just like how we print the black and white normal A4 sheet print, or the color printer where the ink used in the printer. Similar way we can make the organic molecule as a ink, and we can just print it on a surface, maybe on a paper or any other material where the ink will go and sit properly, adhere properly. Or we can even make them to coat, make a thin film just like with a spin coating. Like means if you drop one drop of the molecule and we make a flat surface to spin faster, the drop which is in the center, it will spread like a very thin layer. That is called spin coating. Just like painting, just to put one and just spread data can, or we can even you can take molecule, organic molecule liquid, and we can just coat it. Okay, that is called painting. That means we can put the electronics on a flexible plastic. Electronics is now made up of the electronic main component is our organic molecules. Okay, so we can make it as a flexible plastic, that is bendable displays, smart labels, wearable patches, can be made so easily with organic semiconductor. So it's so special. You don't always need a very hot or expensive steps which is used in silicon chips. Silicon chips manufacturing, if you check, you can see it is the way how the silicon chips are made. It needs high temperature. The method of making the silicon chips are very expensive compared to the simple printing or coating or painting. Now, what is the trade-off? What we have to adjust? The organic materials, they often conduct electricity in a very slow rate right now, and it can be sensitive. The organic molecules can be sensitive to the air. Air means air contains oxygen or any other chemicals which is present, which may react. Or even the contains moisture. Air contains moisture, water content, which will create some issues, which will react with the molecule, or it will make the, because water content, if it is there, we know water is a good conductor of electricity. Therefore the semiconductor work it will be affected. So what we need to protect the whatever the coating that we made, or the semiconductor, with some encapsulation. We need to give some cover, a coat, just like a raincoat that we use to protect ourselves from rain. Same way we need to have a something to cover that, but still the system is working. Now p type and n type, which will move easily, question given here. Okay, so electric current is just the charge moving. Either it may be the electron is having negative charge. Okay, it may be the electron moving, and if electron is not there at a given position, that creates a hole there. Something is not there, that creates a hole. That is called the absence of electrons. The absence of electrons we always treat as a positive charge, opposite to the negative, that is positive charge. Now the two types, that is the p type as well as n type, the holes moves easily. That means the positive like carriers are moving fast. Or think about n type, the electrons moves easily. That means negative carriers are there. Therefore we have p type devices which have the holes are moving easily, and we have n type semiconductors in which the electrons are moving fastly. Okay, so in a device we can try to make it easy for the whatever the charge carrier that we wanted, either it may be a electron or a positive charge. that we can do to enter the material from a metal contact and move across it, so that we can manipulate it, we can make it as we wish. Okay, now how the things work, how the where the electrons are staying. The electrons may be there in the highest occupied molecular orbital, that is HOMO. That is a top shelf which is already have electrons. Okay, this is about molecules. Let me tell about atoms first. We know atoms are having a positive charge center, nucleus, and the electrons are revolving around those positive charge center in different layers. Okay, okay. So different layers are there. The electrons at the topmost layer are always free to move or free to react. Okay, when it comes to the molecules, atoms combines to form molecules, then become molecular orbitals, not atomic orbital. The molecular orbitals. So molecular orbitals when it comes, they have a HOMO as well as a LUMO, that is highest occupied molecular orbital as well as the lowest unoccupied molecular orbitals. Okay, when we say lowest unoccupied molecular orbital, it does not mean that it is having a low energy, but actually it is above that of HOMO. So the electrons are there in the highest occupied molecular orbital, means it's the top shelf which already has the electrons, and the lowest unoccupied molecular orbital means it is the next shelf above the HOMO, that is empty and ready to accept the electrons. It is free and is capable of holding the electrons. We call it as a lowest unoccupied molecular orbital. So if it is easy for an electron to jump up into LUMO, lowest unoccupied molecular orbital, and move from the molecule to molecule. Okay, the electrons are jumping from the highest occupied molecular orbital to a lowest unoccupied molecular orbital, which is capable of holding the electron or taking the electron, having the same state of holding the electron what the HOMO is having. Then the electrons can jump to the LUMO, and when it jump to there, it is having more freedom to move from molecule to molecule, just like from our regular state, comfortable state. When we go out, we have more freedom to move. When comfortable state, we think whether to move or not. Same way, when the electrons go to a LUMO, it has got more freedom to move and it will move. So it is easy to remove an electron from HOMO, leaving a hole. And once a hole is created, that hole is also having a freedom to move. Okay, let that hole to move along, the material behaves p-type. So if electrons are moving, it becomes n-type, and if the holes are moving, or it is called as a p-type. Okay, now the size of the HOMO LOMO gap. Okay, there is a energy gap between highest occupied molecular orbital and lowest unoccupied molecular orbital. It is like how tall the step is between the shells. A smaller gap, if it is there, which makes the conduction easier. That means we need a less push or less voltage. If it is a bigger gap is there between those two levels, energy levels, then it needs a more push, more energy need to be supplied to make the electron in that particular molecules uh, to make it move from one molecule to the next molecule, so that when movement is there, we can say conduction is there or electricity movement is there. It is possible. Now, how do the contacts, metals, and barriers fit in? Okay. Now, how to provide that extra push or the voltage? We cannot directly connect the electric wire to the organic molecules. Okay, we need something to in between to support that. That is metals. We call it as metal contacts. So to get the current or the charges to enter the organic thin film, a metal electrode like the gold or aluminum, they are used. Whether that is easy or hard depends upon the energy alignment. Whether which particular metal need to be used, that also need to be studied and need to be established. Okay, not that every time we can use the iron metal as a contact or the contact metal. So a metal has a number of called the work function, how tightly it holds its electrons. If the metal's energy it lines up nicely with the highest occupied molecular orbital of the molecule, it is easy to inject the holes. It's a good for the p type. If it lines up better with the lowest unoccupied molecular orbital, it is easy to inject electrons. We know when electrons are going to lowest unoccupied molecular orbital means they are electrons. Electrons will move. It becomes n type. Okay. If the highest occupied molecular orbital having a hole, and it is easy to move, then it becomes a p type. So whether the electrons in lowest unoccupied molecular orbital is easy to move, or the hole created in highest occupied molecular orbital is easy to move, that depends on the metal's energy. So if the alignment is bad, the charges face an injection barrier, which is a barrier. It's difficult to overcome. So the electrons will not move, or the positive charge will not move. So engineers, they often add ultra thin helper layer to lower this barrier. Okay, so you can think of a truck which is trying to roll the load to dock onto a platform. We know how the truck will do that. It will bend its and it will try to dock. So we can think about a charge, metal, and to a organic semiconductor. If the dock height it matches with the platform, then the rolling is very easy. If the dock height is not matching, then what we need to do, we have to keep some ramp. Some ramp we have to keep, and we have to allow that dock to move to the platform. That is called as interface layer. For more push needed, we have to push it to fall on the platform. That is, we have to give higher voltage. So either interface layer required, or we have to give higher voltage in such cases. Now putting all these whatever I discussed together, why one organic p type and another is n type? Okay, examples are given. Molecules of pentacene. Pentacene is a molecule. Perfluoropentacene is also another molecule. I'll just show you the structure, molecular structure. So this is called pentacene, which is having all hydrogen. The structure full contains carbon. Every corner is having carbon, and wherever possible, hydrogens are there to occupy the four valence vacancy of carbon. Wherever possible, here all these sides we have hydrogen were not on the junction. There is no need of no hydrogen present, only carbon is there. Tetravalency of a carbon satisfied at center, but here at this particular point, which you can see, I think cursor is visible to the thing. At this particular point the hydrogen is there, at this particular point hydrogen is there, this point the hydrogen is there. Okay, wherever you can see the fluorine atom connected, those places actually in this pentacene having hydrogen, but usually when we write the structure, molecular structure, we won't show it. Okay, so this is pentacene and this is perfluoropentacene. Okay, so two molecules are introduced here. So pentacene, which actually give p type, it is the structure you can see, it's a flat sheet like molecule. It can be stacked. You can keep one pentacene molecule above the other pentacene molecule. You can keep stacks. Just like we keep the CDs or the biscuits one over the other. Same way we can stack gold. Okay, let us think about this. Gold plates we keep one over the other. We call it as stacks. You can stack the pentacene molecule very neatly, and it is easy to remove an electron from the highest occupied molecular orbital of the pentacene. So when we remove the electron, when we are thinking about the movement with the highest occupied molecular orbital, means it is the hole created when the electron jumped to the lowest unoccupied molecular orbital. So it becomes a p type. Get it? So that means the holes can appear and it can move from molecule to molecule. So pentacene naturally behaves p type. So example is given, example device, a pentacene transistor, organic field effect transistor. OFET means organic field effect transistor. Field effect transistors you might have heard of. Field effect transistors means the movement of electrons is affected with a field, and if the field is created with an organic molecule, we call it as organic field effect transistor. Okay, so a pentazine transistor with a high work function, a high work function metal contact if it is given, often gold is connected as the contact. It will inject the holes easily, so it becomes a very good P channel current. It becomes a very good conductor of the holes, or becomes a P type semiconductor. Now let us think about perfluoropentazine, that is N type, with the fluorine atoms added. That is structure I have already seen shown. This is the perfluoropentazine. Okay. Uh, Now the fluorine, it will pulls electron density. Fluorine has got the structure of fluorine you might have studied in lower classes. So the properties of fluorine. That properties of fluorine only used here. It can pull electron density, so which will lower the lowest unoccupied molecular orbital, which will brings that empty shelf down in energy. It will pull energy, means the lowest unoccupied molecular orbital become more accessible, more easy to take the electrons. Okay, so with the lowest unoccupied molecular orbital easiest to reach, the electrons now can easily hop along more easily. Then it becomes a n-type behavior, because the electrons in are easily going to LUMO, lowest unoccupied molecular orbital, and they are free to move. Electrons are moving, then it becomes n-type behavior. Now example of device is a perfluoropentazine transistor with a low work function contactor, which gives the electrons more easily. It injects electrons into LUMO and becomes a good n-channel current. Now how actually the charge actually moves in organics. In many organic semiconductors, the molecules are held together by relatively a weak force. So the electrons and holes, they often they hop, they jump from one molecule to the next, not a free movement. The electron has to overcome a small barrier and it has to jump. It's called as hop. It hop from one molecule to the next, like stepping stones across a stream. Okay, when we cross a stream, we will not to wet our legs, so we will jump from one stone to the next stone. In the similar way, the electrons will hop from one molecule to the next, rather than they freely flowing, zoom through a highway. So how easy that hop is, it depends upon the packing. Flatter, well stacked molecule, easier hopping. The packing of the molecules, how the say pentazine or fluoropentazine, they are closely packed. If they are closely packed, it is easy for the electrons to jump. Okay, so it will be easier for the hopping. How purity and effect. If while packing or while they kept together, if anything is there in between, which will hinder the hopping, which we call it as the impurity are there, uh, then the stones are missing. The actual stone which is needed, it is missing, and only mud is there. We cannot jump onto mud. We'll go inside. Okay, so such type of impurities are there, then the electron movement will be blocked, or it will slower the path. Yeah, it will take time to jump to the next stone. So the purity and defects also affect on the movement of the electrons, or even movement of the holes. Then moisture and oxygen, it can create traps, potholes, a big gap it can create. The moisture oxygen can create such a hindrance. Now the temperature, a bit of warmth, it will be easy for the electrons or the holes to jump. Too much will actually damage the molecule. Organic molecules, it will undergo changes when high temperature is there, but little bit high temperature than normal room temperature, then it will be easy for the electron or the hole to move. Now third topic, the types of organic semiconductors which is used in this type of memory. I've got three types, that small molecules, conjugated molecules, and ferroelectric polymers. All three types are carbon based, which the material we can lay down as a thin film, even by printing, just by coating, or there are so many methods of preparing thin films, dip coating, or spin coating, or solvent evaporation, or even painting, printing. So many thin film formation methods are there. All these methods can be easily used in this type of semiconductor materials devices. So we use them to build a tiny switches which can remember 0 or 1. So these differences are in how the molecules are shaped and how they hold or flip the charges. So we'll see one by one. Small molecules that is given in the syllabus, that is pentacene and perfluoropentasines. Two examples are given in the syllabus. Okay, so what are they? Just think about flat tiles. Okay, let me give bullet point. Okay, so think of a flat tile, a flat molecule, which is stacked very neatly like sheets of paper in a pile. Because they stack well, the charges or the electron or hole can pop from one tile to the next very easily. Why the memory works here? When we built the transistor with these molecules, that is organic field effect transistor, we can write a bit by pushing a little extra charge into places where it likes to get stuck, called the trap, near the interface with the insulator. That means uh, we can make the movement of electron or the hole to a certain level where it go and get trapped. The trap is also we only created in that molecule. That means it will, we are making the molecule to move to some extent and making it to stay there. So these trapped charges, it will shift how easily the transistor turns on next time. This shift is the stored bit. Okay, that means we are giving an information or we are making the electron to move or the hole to move to a certain extent and making it to stay there. It will stay there for a long time. That means we are given some instruction, we are given some feed, and that feed is recorded like that, that movement. Okay, that is a memory actually. Okay. Uh, Two famous examples are given, that is pentacene, which will make the holes move easily, and perfluoropentacene, it will make the electrons move easily because the fluorine atom, it will pull electrons. Now how it looks as a stack, simple sketch. It's the layer. There is a lower layer of metal gate, there is an insulator, there is a small molecular layer of pentacene, and there is a source drain metal contacts connected to that in between. So you know the structure of a transistor, that the diode, those structures you have to think with this type of. You could have given the same picturization. Could fail to do that. Okay, I didn't see that. Okay, simple sketch I could have prepared. Okay, let it be. Okay, how it looks like, we know how does it look like now. Now the advantages of this type of small molecules as organic semiconductor used in a battery. Mm, Advantages: they often high mobility among organics, so faster switching than many polymers. It can be vacuum deposited films, can be very neat and uniform. That means good paths for charge. Limitations: some n-type small molecules are sensitive to air and moisture, so we have to add a protective coat. Extra work is there. Films can form grains like tiny crystal islands. Okay, small gaps, so small gap islands can be created. The edges can slow, and those it can slow down the movement of charge. Now, where it shows flexible sensor tags, simple logic and memory on plastic, interface, charge trap memories for demos and teaching kits. There we can use these molecules, pentacene, perfluoropentasene as a organic semiconductor material. Now, second one, that is conjugated polymers. Example is poly-3-hexyl thiophene. They are just like cooked spaghetti, long flexible chains. So these chains are conjugated, which means the electrons can move along them more easily than in ordinary plastics. Conjugated means they have alternate single and double bonds. That is actual meaning of conjugation. Alternate single and double bonds means the pi electrons formed. They are easy to break. We know how the pi electrons are formed. We studied the covalent bonding, pi bonding. The pi bonding formed, and if it is alternate pi bonds are there, pi bond can open, it can connect to the next carbon, a new pi bond will be formed, and it will keep on shifting and will come back. So that is called the conjugated effect, conjugation effect. So if since the chains are long chains and they are having conjugation, alternate single and double bonds, the electrons can move very fast, very easy. No need of hopping also. Okay, so why memory works here? The polymers are they are inkable. We can make them as a ink. We can spin coat them or we can print them from a liquid. In a memory transistor, we can again trap the charge near the insulator, or we can use a polymer electrolyte, a layer which hold charge like a balloon holding the static energy or static. Writing, that is push in charge, erasing, pull it back. So whenever we want to write, we have to push, give the energy. When we want to get it back, we have to get the energy from that. Then it will write and erasing can be done. Now how it looks, again the schematic representation is how given: metal gate, insulator, polymer film, and source and drain. Similar way, the so small molecules how they look the same way, it also will look in the same way. Now advantages of this conjugated polymers as a semiconductor: they are very scalable, they cover large areas, therefore it is great for displays, labels, posters with electronics that we make. Now you can see everywhere the posters are not the plastic printed posters, electronic posters are there. So there we are using this type of molecules. Low temperature processing, it works on plastic and even paper like substrate at a very low temperature. Limitations, they usually slower than the best small molecule. The charges weave through that spaghetti. Film quality depends on the solvent, the drying method as well as the alignment, and the results can vary more. Where it shows up, it shows up in printed electronic also large area sensor arrays with local memory, low cost disposable or wearable devices it is used. Now the third one I will complete this one and stop. I'm tired. I need rest. Okay, ferroelectric polymers are the third one. Example is given: polyvinylidene fluoride trifluoroethylene, that is PVDF TRFA. What are they? They are very tiny compass needles, dipoles inside a polymer. They are having the magnetic type of behavior. They work like a magnet. With the electric field, we can point all the needles either to left or to right. Okay, and they will stay in that position for a long time. That means it becomes a stable, it becomes a non-volatile. It is volatile means it will evaporate easily, non-volatile means it will not evaporate. Okay, so it becomes non-volatile memory. We heard about volatile memory and non-volatile memory. This type of materials, it can be used as a non-volatile memory material. Now, why memory works here? We put a ferroelectric polymer next to a semiconductor channel, which is a small molecular polymer, and when we program it, we will flip the dipole. We flip the charges to one side, so all the molecules will flip to one side. The electric field shift the threshold of the transistor. The electric field so that when we come back later and read, the device will behave differently depending on the previous flip. That means we have stored 0 or 1. That difference is called as 0 or 1. Okay. Now two common devices which are used with this type of ferroelectric polymers are ferroelectric field effect transistors. The gate insulator is ferroelectric in that, or capacitor type memory. It will just store polarization in a ferroelectric capacitor and sense it. Okay, the polarization means the movement of the what is that flip, that we said the molecular flip, that is actually called as the polar because of polarization. Polarization means charge separation, pole formation, different poles, positive and negative poles formation. We call it as it has got a polarization is there. Okay, so How does it look like? Again, same concept. Metal gate, ferroelectric, PVDF, organic semiconductor, and the source drain. Now, advantages of the third type of that is ferroelectric polymers as a semiconductor device. It has got, it will remember the output power. It is a non-volatile one. Low voltage switching compared to many charge trap schemes. It often fast enough for embedded or low power memory. Embedded system, we know it, many devices, many small electronics gadgets are made work together. We call it as embedded system. Limitations, it can show fatigue, that is a property which slowly charge after many flips. The charge slows, the work it will the flip it will slows down, becomes fatigue, it becomes lazy after sometimes we call it as fatigue. It needs careful processing for uniform films as well as to get stable behavior. Now, where this ferroelectric material shows up, instant on, flexible badges, low power ID tags, small embedded memories in wearable systems where we are using ferroelectric materials. Now, why we pick organic at all? Whatever we discussed now, other than silicon, we said it is organic. Make on plastic, light, bendable, even rollable devices. We can print like graphics, you can cover posters, windows, packaging. You can have smart bandages, e-skin, labels that lock temperature shocks, and even wearable packs. The e-skin, these things, it will come when it goes to the robotics level of thinking, where we need the movement of electrons through the skin. Then we know our body, there are skin is used for many type of movements. Same way, e-skin is that concept that it goes to higher end thinking of robotics type. Now the trade-off, what is the problem with that? It often slower and less stable in air than silicon or oxide chips. We usually add encapsulation, thin barrier coat is needed, and choose better contact to protect and improve the performances. Okay, so till fourth topic I have discussed in this particular class video. That means I have covered memory devices, P-type semiconductor, and N-type semiconductor. Till here, the difference. Okay, I didn't cover that. I reached till here. Okay, okay, that's about this particular class. Uh, till perfluoro, this one I have covered in this particular. So I will cover the next one in the next video. Thank you very much for watching my YouTube channel and supporting. Once again, thank you.